Okay, so now we're going to consider the Mandela effect and changes that could be caused by activity at the Large Hadron Collider, CERN, and how quickly those changes can be felt across the whole planet. We're going to consider something really small because obviously the computing power needed to calculate how quickly something like that can spread through all the atoms in the universe is beyond me. I'll probably need to be at CERN to be able to to calculate that. So basically, the way I'm looking at it, if there is a change happening at on an atomic scale, I will consider force. I'm going to use the force. It's not a Star Wars pun. I'm just going to use force to illustrate what I mean with Fibonacci sequence. Fibonacci sequence. I know I used to call it Fibonacci. I swear it was Fibonacci, but Mandela effect, Fibonacci. So Fibonacci sequence will be used with the force to explain how it's possible for CERN to do something and then unwittingly for that to actually manifest into a Mandela effect. Now if you look at the average distance between two atoms in outer space, it can be as large as a meter. I didn't know that. That's weird. But on Earth we use the atomic unit of length, the bond length, which is the Bohr radius of 52.9177 picometers, and that's every covalent ionic bond or whatever type of bond there is on Earth is within, I would say, 5, 10 to 100 of these units, of these atomic units. Yeah, atomic unit of length. Yeah, probably 100. Like the carbon to oxygen bond, the distance between the carbon and the oxygen there is around 4 times that. But I'm going to use that for this argument. And then if we assume that all force moves at the speed of light, because light is made of photons and photons are force carrying particles. So let's say all force moves at that speed. Yeah. For argument's sake, but I do have a disagreement, but I won't go into that. So that's why I'm using the speed of light. Now, the average time taken for a force from one atom to impact another atom, let's say you're an atom in space, and then your nearest neighbor is 1 meter away. Yeah. Now, and then you exhibit a force. Let's say you move sideways. Yeah. Now your neighbor who's 1 meter away will experience a change in gravity, in the gravitational field, and I think because it's 1 meter away, that change will be 1 meter divided into the speed of light. That much. That's how long it will take you to sense that. Well, your neighbor has suddenly, for your neighbor to sense that. Well, you've changed position here. Yeah. So non-living things detect themselves anyway. So they use the force, you see. So anyway. Damn. So but we're on Earth and we're using the Bohr radius. The distance between two atoms on Earth, I'm gonna assume to be 1 Bohr radius. Just simpler that way. I can't be bothered to calculate the average. So, and the speed of light is the same, and that's the time taken if one atom was to experience a force. For all the atoms in a on Earth to experience it, they'll need to be traveling at that speed. So the next atom to experience it will take that long, and the next one after that long, and so forth. Yeah. For argument's sake, let's say you're in a column. I don't know. Right. So the average number of atoms in the observable universe is 4 times 10 to the 79 to 4 times 10 to the 81, and that's too much for my computer. Like I said, I'll probably need to be at CERN to be able to calculate how long that would take for the universe to experience what they're doing down there. But let's start with a human cell. It's not 100. There's 100. Let's say there's on average 100 trillion atoms in a human cell. Yeah. If there's 100 trillion atoms, and one of those atoms within that cell experiences a force, the next atom would acknowledge that much time afterwards. Yeah, if you look at this time here, and go to my Fibonacci sequence, that's the time you see right at the beginning there, 1765 times 10 to the minus 19, which is that there. Yeah, so one atom would experience that, and that's how long it would take. Two atoms will take twice as long, this Fibonacci sequence. Three atoms will take 3 times that, 3 times as long. Yeah. 21 atoms will take 21 times that, which is 21 times as long. Yeah. So and so forth. Now, by the time 100 trillion atoms has felt it, yeah, we'll get up to 68 stage, the 68th number in the Fibonacci sequence. Yeah. Between 67 and 68, that's 72 trillion, that's 117 trillion, and that's 73%, that's over 100%, so somewhere in between there, which is a total of 2.077 times 10 to the minus 5 seconds. Yeah, that's how long it will take for 100 trillion atoms to feel a change that has occurred in one atom. Yeah, that's like 10 microseconds. Yeah, to cover 10 microseconds, that just to do 100 trillion atoms. Now, to cover the whole of Earth using the Bohr radius, if it takes 10 microseconds to do one cell, it's not going to take very long to do a whole body, a whole planet. Yeah. Like I said, I don't have the computing power to do it, but I would imagine it's a couple of days. Yeah. It might even be a couple of hours, looking at that. Yeah. No, it's a couple of days. There's quite a few number of atoms on Earth. There's probably 10 to the 50 atoms on Earth. And this is on the 10 to the 12. So it'll be a few days for one change at CERN to be felt by all the atoms on Earth. Yeah, but it is possible that they can do something that will cause a change in one atom that can start to change all the atoms around CERN, and then beyond CERN, and then across the whole world, and then when it gets into space, then it's limited by this fact, but the Earth can be covered pretty quickly by any changes that happen at CERN. But I'm using Fibonacci sequence here to say that basically the changes occur sequentially, according to this sequence here. Yeah, and they occur in different stages. So it's possible for CERN to be responsible for the Mandela effect, but like I said, this is just a theory. Take it with a pinch of salt. Again, if we do have CERN firing up and then we wait a couple of days, we'll be able to get a much more accurate view of what's happening with that. If they do something that does filter through, is something that we'll be able to see in our lifetime, because there's enough atoms on the planet, like 10 to the 50, but the speed at which these things happen is so quick that we'll be able to observe it within days, at most weeks, I would say. Yeah, so I won't rule that out if I was you. Yeah. Again, be vigilant, watch what they're doing, but they're not the only people that can cause these changes. There's also changes in outer space that can happen, that can travel so quick that